There she is.
Thanks, Scott. Okay, hi everybody. We're almost done. The food smells great. You're almost there. All right. So far we've talked about the many benefits of this project. Everything from job creation to increased national security to the mitigation of climate changing emissions. But there's one thing that might be stuck on some of your minds, and that's how do we take this great idea and turn it into reality? So that's what I'm going to talk about today. How do we begin the implementation phases of this project? And the answer is by utilizing feasibility analyses to take real environmental and engineering challenges into account. One of the ways that we do that is by preliminary siting, using trusted data from public sources to figure out where and why we place HVDC cables in certain locations. Preliminary siting has a few different benefits that I just want to quickly run through. The most obvious being that we can weed out locations that might not be so viable up front, so we can manage our time more effectively and spend time siting areas that we already know are probably going to be viable. We can also mitigate potential negative externalities by taking into account environmental or political challenges that might arise from placing cables in certain locations. If we know up front where sovereign lands are located or which areas constitute some sort of biological conservation status, we can either work with those groups up front or mitigate and move around that land if possible, and that streamlines the construction process down the road. And lastly, we can do our due diligence to make sure that we're integrating existing infrastructure. This means current HVDC cables, potential renewable infrastructure that's already present, and utilizing right-of-ways that we know are going to be effective. So as we're going through and we're siting, one of the things that we focused on most importantly was soil conditions. This was really crucial because most of this grid we're hoping to place underground. Soil can affect the grid in a couple of different ways. Most importantly, it can affect the electrical or the thermal resistance of how cables function. What I mean by that is when cables are buried in the ground, you can either impact the way that that current flows through the cable, or you can impact the way heat moves away from the cables. Both of those conditions have to be optimal to make sure that we're operating at efficiency and that we're operating safely. So looking at all of these different soil variables, we're going to look at that in our first of two case studies that I'm going to talk about, called the Western Pilot Project. This is a project that spans the westernmost 11 states of the country, from the Pacific to the plains. And the reason we focused on this region in particular was because of the renewable goals of California. They have a 100% renewable goal, and we think that that need will anchor the need for this system in particular. We also know that there's a lot of existing renewable infrastructure and also some HVDC lines already in this region. So a lot of you might be shocked by the size of this potential pilot, but we really think that that's essential to showcase how resilient a grid can really be. We also wanted to make sure that when we were doing all of our methodology that we took as many geographical variables into account as possible. So as we were looking at the different environmental variables, one question came up again and again, and that's how do we know if we're placing cables above ground or below ground? And we got the answer from looking at variables from public sources like USDA, USGS, EPA, et cetera. So as we were looking at these, we found that variables typically fell into two different categories, which we called either amend or avoid. Avoid variables are things that are very extreme and can make undergrounding cables either challenging or even dangerous. These are things like Superfund sites, existing fossil fuel infrastructure, or shallow bedrock surfaces that make it very hard to drill cables into the ground. So when we hit any of these conditions, we automatically placed cables in an above ground configuration. There are also a second category of variables called amend variables, which are less extreme. These are things that make soil conditions less than optimal, but they can be corrected and we can still place cables underground anyway. These are things that mostly have to do with the physical or the chemical components of what makes up a soil. Whenever we deal with conditions that are less than optimal, we typically either mix in other native soils from the area, or we can even use artificial fills to make those conditions optimal to where we need to be to get proper current flow and proper heat flow. So combining all of these variables together, we came up with a final picture of what the Western Pilot Project might look like if it's actually built. You'll notice that this system follows pretty closely the major highway system in that area, and you'll notice 3 different colors on this map. Those areas that are red constitute those avoid areas where we automatically place cables underground because they didn't meet a certain condition. Areas that are blue are places where we could place cables underground, but we might need to amend the soil in some way to make the conditions optimal. And areas that are green are places where we might very well be able to place cables underground with no alteration of the environment at all. So what this all boils down to is that 2/3 of this system could be placed underground feasibly in this environment, pretty large amount. And while the system probably won't look exactly like this if it's built, I still think this is a very valuable analysis to help us streamline and refine our costing and also guide our research in the future. So, totally shifting gears now to our second pilot project, we wanted to look at a totally different environmental condition, namely what would it take to place cables in a submarine environment. And we focused on the eastern region of the United States when we were doing this analysis because we noticed a couple of issues with that region. The first being that a lot of the right-of-ways, highways, and railways are very crowded in this region. It might be hard to find the space to underground cables effectively. We also noticed that some of the soil properties were not optimal, so a lot of the system might need to be placed above ground anyway. So we decided to try and see, could we feasibly go along the Atlantic seaboard and place cables underwater there? We also think that this could do a world of good in integrating more offshore wind that is very prevalent in this region in particular. So as we're looking through those environmental variables, we didn't so much have a concern with what's going above or below ground, right? Everything's going to be underwater. But it was more a matter of where should those cables be placed. And in looking at those different variables, we came up with 3 categories with varying degrees of importance. The first and the most important being our primary concerns. These are things that absolutely have to be taken into account if we're going to place cables underwater. These are things like existing military installations or oil and gas infrastructure, conservation areas or commercial fishing areas, things that people depend on for their livelihood or could make the system potentially dangerous if it were to go awry among these certain locations. Secondary concerns are things that were still crucial, but a little bit more variable than primary concerns. These are things like vessel density, which tend to ebb and flow with time and season, or things like wind planning zones or renewable lease areas, things that aren't set in stone yet and may change. And then lastly, we looked at supplementary concerns. These are variables that didn't come up very much in our data sets. And ultimately, we were able to overlay all of this together into this very complicated and colorful, nice map here. So what you'll see is that we see a couple of different gaps happening, namely right here, where we can start to see where a cable might actually be placed to avoid all of those major variables. What we also see is some gaps around New Jersey and Delaware, where we might try to bring that cable and connect it to the remaining onshore grid. And that's crucial to make sure that we integrate that offshore wind capacity to the best ability. So looking at something like this especially, it's very easy to see why projects like this seem daunting and seem impossible. But the reality is that HVDC lines are present and operating right now all over the world. In the United States in particular, there are 7 HVDC lines. Most of them are focused on either the western or the eastern coasts. There are also 5 lines that are currently being proposed or under construction right now, again, in those general regions. While there aren't a whole lot of examples of underground HVDC in the United States, that is the case abroad. An example I'll give is the Western Link, which goes through the United Kingdom, which utilizes both underwater and underground configurations. There are 3 countries in particular at this point that are really leading the way as far as HVDC implementation, those being China, Brazil, and Germany. China in particular has been beefing up its transmission system really since the turn of the century, so much so that 7 of the 10 largest HVDC lines in the world are located in China. And there's many smaller lines supplementing that transmission, bringing in generation capacity from far off places into the major load centers. In South America, most of the operational HVDC lines at this point are in Brazil. And unlike China's HVDC lines, which can carry both fossil fuel and renewables, that's mainly what they use them for, but Brazil's lines mostly carry hydropower. And lastly, Germany is a great example of the usage of HVDC, not only in their own country, but also to connect their energy supply with other surrounding nations. And for the most part, they carry renewables on their lines in particular. So the common thread between all the HVDC lines for the most part in the rest of the world and the ones that we utilize as well is that for the most part, they're not thinking in terms of a network. The prevailing thought has always been to go from point A to point B, generation to load center, with really no regard for how things come together. That philosophy is starting to change, and we as a country have to make that leap. The United States has the potential to protect our country by building a grid overlay that is resilient, that's cost-effective, and that's environmentally conscious. The North American Supergrid integrates all of these concepts together into a single proposal that's timely, that's bipartisan, and that works in today's economy. And that's why we feel that it's one of the most important infrastructure initiatives that's been proposed today. Thank you very much.